Okay, I'm Adrian Cockcroft from Netflix, Cloud Architect, and we have Rosalind Meschenberg with us as well, who's the Director of the Engineering for the Cloud Platform team. I'm going to start off, and Rosalind's going to take it about halfway through and run to the end. So we're going to talk about the Netflix open source toolkit, all of the different tools we've built. There are something like 35 different things that we've built in open source in the last 2 years. And we're going to do it from the point of view of a startup that has a problem. So let's say you're a startup that just got funded. You're going to have more developers, more customers. Now you need high availability, maybe going to go global. But your stack currently looks like this. You did sort of Ruby on Rails, stuck it in one zone, and it's just sitting there. And you've got a few customers trying to get into it. What you really need is something that looks more like this, with lots more customers spread all over the world, going into regional load balancers, multiple zone, multiple region, replication underneath, and a complicated-looking microservices architecture underneath. So how do we bridge those two? Inside each zone, your traffic comes in, and there are lots of different services that are serving it, and you have Memcache, Cassandra, web services, S3 buckets. The whole thing looks much more complicated, and we want to help you get there. And NetflixOSS, we're kind of all the pieces you need to get to global scale. It's Apache licensed, cloud native, open source platform, and it's up on GitHub. The problem is we gave everyone technical indigestion. How many people read the Netflix tech blog posts? Right. How many people have bunches that you haven't got around to reading yet? Because we released 4 or 5 of them in a week, and you can't keep up. And that one looked interesting, but you can't keep. There's just too much stuff. So this is what our GitHub site looked like until a week or 2 ago. We just changed it to make it a bit easier. So now we've got categories, because we're stealing the graphics from our user interface, obviously, from the regular Netflix site. So now we've got availability and all the other different categories as if they were genres. So you can figure out, I'm interested in some particular aspect, and these are the projects that are related to that. And there's some better getting started information there too, and some links. And we'll walk through the getting started process next. So this is what you have to do. First of all, we have our account set up in a certain way, so it's not the only way you could do it, but at least it gives you a baseline for the way we think about running our AWS accounts. We want to get a security and access management set up properly. Then the account management tools go in, Asgard to deploy, and ICE for cost monitoring. Aminator to automate baking AMIs. Then we have a service registry called Eureka, and we put in a searchable account history called Edda, and I'll get a bit more into that a bit more later, but it's a very powerful way to track everything that happens in an account. Next thing is you're going to want to do dynamic configuration management, be able to tweak a variable, change a timeout, turn a feature on or off, and have that scoped across your system. So that's what Archaius does. You obviously need to store some data, so I'll talk about the Cassandra tools we have, Astyanax, which is our Java client library, Priam, that is used to manage Cassandra, and EVCache, that's a Memcached management layer. Then you're going to want to route traffic into this system. This is where Rosalind's going to take over, because he's giving a talk later this afternoon that's particularly about this point. But Denominators for DNS management. Zuul is an API proxy management tier. Ribbon is the client-side calling outbound libraries, and Karyon is the sort of base server that you call into, and all of that, different parts of the framework. Once you've got it working, you need to break it. So we have the Simian Army, which runs some of you probably heard of the Chaos Monkey, that's just one member of that, and Hystrix for making protected calls with a circuit breaker pattern, so you can call dependencies that you don't trust and manage the reliability of them, and Turbine for monitoring those circuit breakers with 1-second updates in real time. And then developer productivity tools. If you've ever run into Log4j logging storms, Blitz4j fixes a lot of the problems there. Garbage collection visualization. Pytheas is for building dashboards. It's sort of Twitter Bootstrap and a whole bunch of things all glued together. And RxJava for doing functional reactive programming. And then if you're once you've built your system, you're generating a lot of big data, you want to process it. So we have a Genie, which is our Hadoop platform as a service that we use to manage lots of EMR clusters. And if you're using Pig, we have a visualization system called Lipstick for that. So we put lipstick on a pig. There we go. And to get you started, there are 3 different sample applications. The RSS reader that we built, it's on our site. Acme Air that was built by IBM. And Flux capacitors built by Chris Fregley. And so we'll tell you how to find those, and they all cover slightly different things. So that's the step-by-step. I'm going to go through and show you what those actually look like. First thing, how do we set up our accounts? Well, this is sort of an abstract way of doing it. We have 4 different accounts, AWS accounts. There's the dev, test, build account. That's where all of the build system deploys code, and that's the only place we deploy code. The only way we get code to the production account is by moving an AMI that's been pre-built, baked with all the bits on it, into the production account. Okay? So we only ever build code in one place, and everything runs there. And there's sort of a complete working copy of Netflix or whatever you're building in this dev, test, build account. Asgard helps you manage different developers so they don't all stomp on each other, and you can route traffic around it with tagging and things like that. So then the production account, it's running, you've got all your nice customer traffic coming into it. You want to do backups of production. So the way we do backups, we take Cassandra and we take all of the backups from there. If you're using MySQL, you can do RDS backups to S3. There's a contributed open NetflixOSS tool for doing that. And you copy them into a separate account, which is set up to just be for S3. There's actually no code running in it. It's just an account to hold S3, and you can kind of lock at the door and throw away the keys. You set it up so that you can write to it and read to it from your production account, and you set the overwrite thing so you get versions. So you can't delete something by overwriting it. So anything you put there will always be there, and you put like a 90-day timeout to sort of remove things after a while. It's a very powerful thing because one of the possible things that might happen is you get account compromise, or some rogue employee or whatever. Somebody gets into your account. They could maybe get into your production account. This is a very safe way of storing your archive, storing your data, without having to go to tape. And you can archive off into Glacier from it if you want. You can set up whatever bucket policies you want. So then we also have an auditable account. That's about, on our scale, the auditing account is a few hundred machines. The production account's tens of thousands of machines. But this auditable account is the only place we put SOX compliant stuff, and we're going to PCI, things that are in scope for audits and compliance. So you make that as small as possible so that you don't have, so that you can do all of your regular, agile or whatever you want to do in the main production account. Again, they're doing backups. And then the neat trick we have is every weekend, we take those backups and we restore them to the test account. So we just overwrite whatever the databases in test had over the weekend when most of the testers aren't there. And you come in on Monday and there is last week's production data sitting there to run all of your tests again. So it's kind of a nice cycle. It proves that you do have backups, because if it fails over the weekend, it's like, oh yeah, we don't have backups of that. That's kind of one of those stupid things you want to avoid. So this is, it's not, it's obviously many ways of setting that up, but what I'll focus on now is this dev test build account and what we put in that. We use the 2-factor authentication to keep our accounts secure. We use IAM to do delegated minimum privilege. This is just basic hygiene, but if you don't get the security set up right at the beginning correctly, it's hard to build, it's hard to add in later. So you should always treat first security as a very foundational thing. First thing you do is set everything up in a secure pattern, and then get people to build within that pattern. It's just way too hard to go the other way. And we use security groups to control which service can call which other service. So that's the basic setup. You want to log into these machines, and we want to audit that you're doing that. So we set up a Bastion machine, some kind of gateway, and get all the developers to log into that. And that machine knows how to sudo into any machine in the cloud. And you can audit who logged in where. And the way that we set up our security groups, the machines in the cloud can't log into each other. So the only way you can get from a piece of, a file or whatever from one machine to another machine, you don't do sideways copies. You come back to the Bastion, copy it there, you copy it back out. So you can actually get a much cleaner view of what's actually happening and the interactions that individual engineers are having with individual machines. So this is particularly useful in this audit account I was talking about, to follow this model and really stick to it. Okay. So tooling and infrastructure. we want to build up a few images to get started with. Peter, who's sitting down here with the yellow jacket on, has contributed a whole bunch of things. He has this little answers for AWS startup that he's been doing. And these are also entries in the Netflix Cloud Prize that we'll be talking about tomorrow in the keynote. He's built pre-built AMIs for Asgard, Aminator, Edda, Eureka, and Simian Army. So you can just go, if you've got an existing setup, you just want to put Edda in your system, you can just go pull these AMIs, launch them yourself, and then you have that facility. So this is a great contribution. But went a bit further than that. He built CloudFormation templates, so you can just walk through and it will install everything, set up all the security groups, and basically create everything for you for these 5 different tools. So we're going to do a walkthrough for Asgard. So this is step by step. If you can't get Asgard running following this, then okay, forget it. Okay, you get the template. You clone the repo. You log in on the console. Go to the page. Then you say create a new stack. Select the template. Let's say Asgard, there it is. Then you want to create the stack, and you have to give the IP address and keys to get access to that. Your IP address, because you want to be able to log into it. Then you create the stack. This step you just skip. Then you confirm that. And then you sit back and watch, and machines appear, and things happen, and it sort of, wait for a little bit. And a few minutes later, it's done. And on this page, there's this, it says PublicDNS. There we are, PublicDNS. That's the address. That's the address of the machine that just got started. So you want to stick that in your browser and go visit it. And then you see Asgard. And this is the startup screen. And Asgard needs to know what your account credentials are because it's going to be running, creating stuff for you. So you enter that. And then it comes up, and this is it. This is, now you can see along the top, you can go, create an ELB, create a simple DB, do RDS, go, create stuff. But then you can give this to your developers, and they don't have to see the account key anymore. Right? So we set this up because we wanted to have something that scaled and something that was more developer-focused than the AWS portal, which is a little more operationally focused. And you tend to get this split where the tooling really is a little bit, and the requirements are a little bit different. But what we do with this is we use red-black deployments. So what we'll do, and this is all built into it, we'll use an auto-scaling group to run one version of our code, and then we'll create a new build, a new AMI for the new code, and we'll bring that into production by starting up an autoscale group. And then we use this page to flip the traffic between them. So we'll turn on traffic to the new code, turn it off to the old one, and leave the old one running for a while. So if it blows up a few hours later or anything goes wrong, we can just go into this and in a few seconds tell the ELBs to switch the traffic to the old code. So this is generally, we use this for stateless services. Most of our service layers are stateless. All our state is in Cassandra or Memcached. So keeping that boundary is another good sort of architectural hygiene kind of thing. So this lets us run really fast with continuous deployment. Every developer is deploying their own code to production using this, and you deploy it to test first, but then we have workflows that will take it into production as well. And we can, if anything goes wrong, you can flip back to the old one. So you can run really fast, and when you get a mistake, it's a really small mistake you can recover from really quickly. And we have sort of 1-second monitoring tools for tracking what's actually going on in these services as well. Okay, so you're deploying stuff, you want to know how much it costs. So we have ICE. This runs off the detailed billing records interface that AWS came out with last year. It's got hourly data. We tag it, we slice it. We generate a report that goes to each manager at Netflix for the stuff that we apportion to their team. So you get a sort of weekly report kind of thing out of this that we do. But the tool itself we've been developing for quite a while internally, and it's got a lot of functionality. So you want to get this running. Unfortunately, it's a little more complicated. We can't do an AMI for this because we used HiCharts as the GUI to do all the charts, and that's available, but it's got a more restrictive license, and we can't package it and put it out for anyone to use. But if you have HiCharts anyway, or you're in non-commercial use, you can just grab it. They give it for non-commercial. And then you build out, there's a bunch of recipes on the GitHub for how to put it together and how to go and run it up. So it's a little bit more complex. We're working eventually to take out high charts and put in something else that is completely open source. And if you want to help us do that, we're very happy. You know, this is all open source. We all help each other. So if you really want to use it and you don't like high charts, go fix it. Fix it yourself. Right. So our build pipeline's based on Jenkins. We use that internally, but we also use it externally. And CloudBees run a Jenkins public pipeline. And one of the nice things is that they provide free use of that service for building open source projects. So if you look at our GitHub site and if you throw a pull request on one of our projects, if you create a pull request, CloudBees automatically gets notified that there's a pull request, automatically does a build, runs all the testing and whatever, and if it passes the tests, then we get notified. The engineer that owns that project or the committers get notified that a pull request passed everything and is built, and we should go look at it. If you throw some code in there that doesn't pass the tests, we don't even hear about it. So you have to get through some tests. Maybe you have to rewrite the tests, but. So this is a nice system, and it's the basis of a lot of our automation. So I've been talking about baking AMIs. We have a fairly sophisticated way of doing that. It's a pluggable, fairly generic build system tool. It's written in Python. It mounts a volume, and basically it takes an existing base AMI, which is usually a Linux build that you keep up to date with patches and things. It takes that and then duplicates it into a mounted EBS volume and sort of cheroots in and then adds all the different packages and things like that, and then snapshots that volume out into an AMI. So it's an efficient way. It's a long-running process, but it sits there spinning off AMIs that are custom-built to do whatever you want them to do. And once we've got these AMIs, we can make one machine out of it, or we can make 1,000 machines out of it. You just say, the autoscaler, just fill in the number, tell it what to do. So if you want to do this, again, there's a CloudFormation recipe, and there are AMIs, pre-built AMIs for it. When you're in the cloud and everything's dynamic, you have to be able to find a service. So I want to look up an EV cache service, but I don't know what the EC2 blah, blah, blah URL is for it and the instances. So what I have is this idea of an application or a service. So I need a service registry. So when the EV cache instance itself comes up, it tells Eureka, our service registry, hey, I exist. Here's a bunch of metadata about me. Here's my IP address. Here's all kinds of information, what ports I'm listening to, what kind of things I'm doing. In this case, it would be 112.1.1, which is the memcached port, as well as the Tomcat server that we use for managing on our memcaches. So that comes up. Eureka now has an entry for that. And everyone now goes and asks Eureka, so where is everybody? Give me a map of the world. And what you get back is, at some point, these are the EV cache instances that are in this zone. These are the ones that are in this zone. You can see here we have some in 1C and one in 1D. So there's a bunch of them scattered around. You pull them in, and you can then see what you're doing. And you can find them, and you have sort of an in-memory lookup that's being refreshed every 30 seconds for where everything else is. Again, there's an AMI, or you can use CloudFormation to start this. The way this is built, it's actually a Tomcat server with a REST interface. You can go connect to it with just about anything. We have a Eureka client library that talks to it. But the server then replicates it. So in each zone you're running in, you run a copy of Eureka, and you configure them to cross-replicate. So the way this works is, on the left we have an application service that's just come up, that's going to register with the server to say, I exist, with the discovery service. And it's going to renew it every 30 seconds, say, I'm still here, and I'm ready to take traffic, I'm healthy, or you could be saying, I'm not ready to take traffic yet. I exist, but my code isn't initialized yet. And then that data is then replicated to the other zones. So then you've got the people trying to call that service, the client, 3 clients at the bottom. They talk to Eureka. They have this map of the world that tells them where everything is, and they can call across to call that service. So that's how it works. There's no intermediate layer. It's not like a sort of kind of Heroku, Cloud Foundry kind of thing where there's this messaging layer that you talk to that mysteriously pops out somewhere else. This is just HTTP access directly to the endpoint on the instance, but this is the mechanism we use for finding everything. And we can make it a little more efficient because we don't just publish this is the URL like we would with DNS. We actually publish much more metadata. Which zone am I in? What's my actual IP address? So we can actually short-circuit DNS lookups and things like that because we can just go straight to the IP address. So one of the things that the service registry does is track everything you've got running, but it changes over time. And then there's all these Amazon entities, and they're changing over time. And then you're looking at some problem that happened last week that you're trying to diagnose what really happened, and half the machines aren't here anymore. And those services are all different, and there's different versions. And so the question becomes, what is the state of the entire environment a week ago, or a month ago, or yesterday, or 5 minutes ago? And what you can normally get is the state of it now. So Edda is a service that basically, think of it as a timestamped Delta store. It does describe calls against all of those Amazon things that you have. You know, instances, ELBs, autoscaling groups, all of those things. It just runs describe over and over again. And then it looks to see whether the previous copy it had, previous describe return was the same or different. And if it's different, it stores the new one with a timestamp and keeps the old one. So now I've got a complete history of the state of my cloud. And this is a very, very simple concept, but it's an incredibly powerful one because we have monkeys running against this, like janitor monkeys cleaning up things that aren't in use, that haven't been in use for a week. And we know because we have the history. You can build all kinds of automation on top of this, and security, things like that. You know, there's quite often you want to find out things like, someone says, there's an IP address that was like spamming my account yesterday. It's one of yours, I think. And you go, okay, well, let's look that up. Let's find all the instances that have ever had this specific public IP address, and you get back a JSON array that has them, and you can go and dig in and get more information about these. But this is the basic thing. This is since the dawn of time, in this account, this is all of the instances that have ever had that IP address. And those kinds of things are very useful. And then showing the most recent change with security group. So there's a bunch of different things. It's a HTTP sort of query language. This version that's currently up there, I think, is the first version we put up there. It has MongoDB behind it because that's kind of a JSON indexed database. It's what Mongo's good at. Internally, we're using one that's using Elasticsearch, and I'm not sure if we've updated the site yet. I should go check. But yeah, those are kind of, it's an indexable, searchable system that accumulates a bunch of JSON. Actually, with the new announcement this morning of the auditing of APIs, that's interesting because it gives you the API, who called which API. It doesn't, and this gives you the state history. So it might be interesting to cross-correlate. We're going to look at how we can combine Edda with the new, what do they call that thing? CloudTrack, or something like that, yeah. Okay, so now we want to look at properties. We have a console where you can go and say, here's the scope. Within this region, I want to set this property to this value. And in Europe, I want to set it to a different value. Say it's an S3 bucket endpoint, and I want the European endpoints to go here and the US ones to go here. So those kinds of things. It's the same code, it's the same AMI, but I'm not baking things in. And I haven't got little XML files lurking on the hard drive. I'm dynamically loading all these properties. It's a bit more sophisticated than that. It's based on this composite configuration. So there's a layer after layer. So you can put defaults in there, and the defaults sort of stack up. And you've got runtime, there's persistence. The system we've got here, unfortunately, that console I showed you, we haven't actually got around to open sourcing it yet, this one. But we'll get there. This is based on this Pytheas console building sort of tools kit that we've got. And the version that's currently open sourced uses SimpleDB or DynamoDB to hold all of the data, the property information, because that's a trivial way of doing it, and it's one of the first things you want to bring up. So you want to configure your databases using this, so you end up with a circular dependency if you have to install a database to control a database, right? We use Cassandra, a version of this that uses Cassandra because we want multi-region support, so we have European, US kind of things. So data storage. Lots of options here. Asgard has direct support for creating RDS MySQL instances. DynamoDB is a great place to start, particularly if you're that startup I was talking about at the beginning and you're starting small. DynamoDB is very simple to set up, scales up from a very low cost base. Like if you only are doing a very small amount of traffic, it will cost you very little. And it's only when you get to enough traffic to be several instances worth of capacity that Cassandra really kicks in. So there's sort of a cost curve for DynamoDB that's sort of a little bit steeper than Cassandra, but there's a crossover point at which it becomes worth running Cassandra rather than DynamoDB. And that's where you've got more than a handful of machines in a cluster to keep them busy. We're now at the point we have thousands of machines running Cassandra and 60 different clusters, and 40 of them are multi-region. And it's kind of a little bit more crazy, but that I think is a different talk this week. So Cassandra has this nice thing that it's now portable, so you could actually have one Cassandra cluster in your data center, one on one type of cloud, one in another region, one in another cloud. It doesn't matter, and it'll do replication across all of them. We're doing it currently between the East Coast and the West Coast, and Rosalind will talk more about that. It also supports incremental immutable backups. The way Cassandra writes to disk, it writes immutable files that don't get modified. We pick those up and we put them in S3. That's how that backup to S3 thing works, and Priam does that for us. So Priam is the deployment automation for Cassandra. So we can create a Cassandra cluster that's arbitrarily large in about 10 minutes per region. So you have to click a bit again, different region to set it up, because we're setting it up in 3 zones. So in 20 minutes, we actually created a 200 terabyte, 96 node cluster across between Oregon and Virginia for benchmarking. That was 20 minutes work. 20 minutes before it was actually running and we could write stuff to it. Sorry, not 20 minutes work. It was 20 minutes elapsed time from deciding to do it to having it. And that's because as the nodes come up, Priam self-organizes them into a cluster. So this is Priam. It's a Tomcat server that runs alongside Cassandra on every instance. It's fully distributed. There's no central master coordination. Every node figures it out for itself what to do. It's S3-based backup, bootstrapping, token assignments automated, centralized configuration management. It pulls out the Cassandra monitoring data and makes that available to you easily. And we put the underlying config for this in SimpleDB, because that's what we were using when we first did that. And that will automatically let you create a Cassandra cluster in a single region, because SimpleDB is scoped to a region. And we actually have a special hand-built Cassandra cluster at Netflix, which we call the turtle cluster, because of turtles all the way down. You have to have something at the bottom. And that is for multi-region. So our global Cassandra clusters synchronize using a special purpose Cassandra cluster that's used to coordinate all the tokens and stitch everything together. But there's no calls across there. You just start a bunch of machines with the same cluster name in Europe as they are in the US, and it says, oh, this is a multi-region Cassandra cluster, and just forms it. It's very, very slick. Okay, client side. Astyanax, which we spell A6X internally a lot of the time because most of us can't spell it reliably. It's the son of the brother of Cassandra, because the brother of Cassandra was Hector, and that was a previous version of the client library that this was developed from. Anyway, and the manager of our database Cassandra team is actually Greek, so he can pronounce all these things correctly. But we took the naming scheme preceded him. So this is a nice abstraction model. It works really well. This is one of the most popular NetflixOSS projects. If you find people using Java clients with Cassandra, there's a large proportion of them now using Astyanax as the core of that. It's token aware, so it optimizes the calls to call the nodes that have the data instead of calling a random node and letting Cassandra figure it out. Lots of useful recipes. So let's look at the recipes. This is where it really starts to get powerful. What we found was our developers were reinventing the same thing over and over again, and it took them a few times to get it right each time. So let's say, well, let's do it once. Let's have a distributed row lock algorithm that everyone uses. And if we find a bug in it, we fix it, and everyone gets the fix, and we're not independently reinventing these patterns. So we have row locks, uniqueness constraints. The chunked and multi-threaded large file storage means that you could actually use Cassandra to replace S3 for things like multi-gigabyte sized files. Because normally when you try writing a huge object into a database, it blows up the one node it's trying to hash that token to. What this does is it chunks it into lots and lots of little things. So it's like, if you used to S3, it's the multi-part write, multi-part read model. It's that, except for Cassandra, with built-in multi-threading. So you can create an arbitrarily large piece of data. It'll spread evenly around the Cassandra cluster nodes, and you can just scale it up. Works very well. Durable message queue is another one. We wanted some behavior that was a little different to SQS. Like you can build a queue here that never throws anything away. SQS has a timeout. After a while, some period of time, your data will disappear. If you don't want that to happen, you can build a durable message queue with whatever syntax you want. So we built that, but there's a few patterns that you run into to do with tombstones and things that you have to avoid. OK. The EV cache I've mentioned as well. So this is memcached in the back end. And then we have this little thing on the side, which is managing talking to Eureka and declaring that it's there. So that's the service side, the EV cache servers. But then from the client-side code, what we published is something that you would use as a developer. And you say, I just want to remember this thing. Here's the key. Here's the value. I just want to store it. The way you set up a particular cache, the EV cache library will automatically replicate that data for you to 3 zones. So now I've got three mem caches, 1 per zone. And when you do a lookup, it will look in the current zone. So you get low latency requests. There's no cross-zone traffic for memcache because your data is right there. But when you do writes, which are usually less frequent, you write across region. Now, it's the eccentric volatile cache or the ephemeral volatile cache for EV. There's no consistency guarantees here. If a write fails, the data isn't there. But it works. This is for in-memory, session state kind of things that are pretty quick. And if you really care about the stuff arriving and being more consistent, then you use Cassandra with its various quorum modes to get the reliable read and write. So that's that. Now I'm going to switch over to Ruslan, who's going to talk about routing customers to code and take us on out. Okay.
All right. So you build up all this infrastructure.
Good, turn on.
All right, so you build up all this infrastructure. Eventually, you're going to have to fulfill customer requests. And let's talk about routing your customer traffic layer by layer. It all starts with DNS. Now, DNS, you typically have a couple of uses of DNS. One, you want to query the DNS information, and 2, you want to control it. And in order to control it, you typically go to your DNS provider's UI console, and you have to do some voodoo magic incantations in order to make things work. And the specific voodoo depends on your specific DNS providers. And so what we build this Denominator library that actually abstracts you away from your provider-specific implementation. It currently supports various providers, including AWS Route 53, UltraDNS, Dyn, and it allows you to do both your read and write operations in a very clean, either command line or API way. And this way, no matter who you use or if you decide to switch, you still use the very same interface, and basically all of your developers and your organizations can do it. You don't need a specialist in order to perform such operation. At Netflix, we actually use the Aminator library for resiliency purposes as well. We don't want DNS to be our single point of failure, and so if we need to make changes in either one of these, in case of any type of fairly drastic failure, if we need to make DNS change, we use the library in order to enact such changes. In this diagram, you see that the next layer down is our Zuul API router. And what it really is, Zuul is a very scalable, very robust, smart routing layer. And it's got fairly complex execution engine inside. You're able to apply dynamically created, dynamically executed Groovy scripts as a pre, at, and post filters. What it means is that before your request is handled, you can apply a certain filter based on certain criteria. During the execution, you can apply a certain filter. And post-execution, you can do the same. And we use the smart routing layer for many, many purposes, definitely for resiliency purposes. We have a talk later today on that. We use it to try and very, very rapid iterations of experimentation for very quick tweaks to UI and user experience. This way, we don't actually have to do full releases and code pushes. Our UI designers can very quickly write a script that will tweak the behavior just right, and then see what the results are. So this is Zuul. Definitely learn more about it at one of our later talks. Next layer down is your client-server communication. Now, as your startup grows, and especially if you embrace service-oriented architecture, you're going to develop tens, perhaps hundreds of different applications. The most important part of client-server communication is that all your applications talk the same language. Otherwise, you're going to have a fairly nasty situation in your hands. If application A talks to application B using one method, then application B talks to application C using another, and so on and so forth, pretty soon you're going to get into a pretty unmanageable situation where if your application A needs to talk to application Z, it now needs to learn a brand new language. Or even worse, if you want to start developing a new application that depends on 4 others, you have to learn 4 different languages how to speak to them. And so we definitely don't want that. We want a common client-server communication mechanism, and this is what Ribbon library is for. All of our applications talk to each other using the Ribbon library, and in addition to providing a common interface, it also provides a common and expected behavior for such client-server communications. It allows you to know what to expect if you're getting errors, timeouts, etc. It also comes with a variety of load balancers built in. It uses Eureka system to get the view of the world, and then uses that view of the world to balance the request appropriately. One of the most useful balancers that we use internally is called zone-aware load balancer. Now, zone-aware load balancer, I want to make it clear, it's not the same as zone affinity. It's very natural for you to feel that if my instance of application A is in zone A, I want to call to my dependency in zone A as well. And that's all fine and great when your dependency works. However, let's say your dependency service suddenly become unresponsive. It's running garbage collection or otherwise erroring out. What's going to happen if you use just pure zone affinity, you're just going to throw more and more and more load to the cluster that's already becoming unhealthy, especially if you have very aggressive retry policy. So zone-aware load balancer takes the health of your dependencies, individual zones into account. And so it's gonna throw more traffic towards the zones that are more healthy and less traffic towards the zones that are less healthy. We've proven that this load balancer works really well in our Chaos Gorilla situations where we take out the whole zone. We'll talk more about it a little bit later. On the server side, the common server-side component is Karyon. Again, in startup life, you're always fighting against time. You always need to deliver a feature. You always need to get the next round of funding. You don't want your developers spending time writing boilerplate code over and over and over again. And so what Karyon allows you to do is takes care of all these common pieces of infrastructure for you on the server side. So if you're a developer, you need to develop a new service, and you start with a Karyon, internally known as base server, because everything for us is based on that. It takes care of really basic things for you. It does all the bootstrapping, dependency, and lifecycle management. It connects to service registry. It lets Eureka know that exists. It connects through to Archaius through the property, and it allows you to manage it via the property console. It has hooks for monkey testing, which is the funnest part. And it also has an already pre-configured status page for its status information, health check services, configuration, etc. So all of these things that are typically you need to implement for whatever service you do, it already has. So this is an example of its status page. It shows you its environment, shows its Eureka metadata information, even exposes the JMX console. The best bit, especially for the developers that are getting used to the SOA, it comes with its own very small hello world application. And so what you can do, you can just take that as a start modifying hello world, you're off to the races. Now, even in a startup, availability is very important, and at Netflix, we definitely take availability very seriously. Our internal goal is to have 4 nines of availability, which, if you do the math, leaves you less than 53 minutes of downtime for a year. So, in order to ensure that your system is available, you have to break it. The choice is yours. No matter how much you test, either users will break it, or you do it yourself. And again, the choice is yours. Do you want the system to break at 3 o'clock in the morning on Saturday, when hardly anybody is available, or at least in the right state of mind? Or do you want to do it Monday through Friday, 9 to 3? This is when Simian Army comes in. We built a variety of monkeys. Probably the most famous member of the army is Chaos, Monkey. And it does what exactly what the name seems to say. It kills instances at random. Each of our application owners can configure it how aggressively or conservatively it wants instances of its application to be killed. But Monday through Friday at random, because we don't want people to prepare for it, instances will die. And we want to make sure that our application service groups are resilient to that, that new instance just going to spin up, that there is no state that crept up into the system, and user doesn't even notice. Now, initially, we were running Chaos Monkey only on our status applications, because that's the easiest. State is hard. As recently as last month, we actually enabled Chaos Monkey to run our Cassandra clusters. And it runs in test and production. I just want to make it clear. It runs Monday through Friday. It kills our stateful instances, and it works. Especially if you run fast, you're going to accumulate some garbage. You're going to run a quick experiment. You're going to forget that instance or a cluster that you created there. You're going to create a whole bunch of data on S3 or pump it into SQS. And you're going to leave it there because your mind's going to be preoccupied with what's next. You need to deploy, you need to experiment, you need to troubleshoot. Over time, garbage will accumulate. And garbage will contribute to your bottom cost line. For that, we have Janitor Monkey. It automatically finds and either alerts or automatically recycles unused instances, ASGs, AMIs, etc. We find it incredibly useful. This way, our developers don't have to spend any time doing the cleanup that automation can. Conformity Monkey is another member of our Simian Army, and it's arguably also extremely useful. It finds and alerts, or sometimes autocorrects, discrepancies between different versions of your applications, AMIs, configuration. Sometimes differences in configuration are on purpose. For example, many of our ASGs are configured to read from different places in S3 or Cassandra in EU versus in US. However, sometimes it's unintentional. Sometimes you meant to deploy the same piece of code in two regions, and yet somehow one of the deployments fail without your knowledge. Conformity Monkey will detect such discrepancy and will alert you if you're running two different versions of the same application unintentionally. And then you can either take a corrective action or you configure the monkey to actually do the corrective action for you. Now, at Netflix, our motto is fail fast, recover fast. And this is where Hystrix circuit breaker library comes in really, really handy. This is a diagram of our API service, and it's dependent, at the time I think it was dependent on 17 other services. In turn, each of those 17 other services was dependent on others. Now, if you think that each of those services provides you with 99% availability, but then you multiply all of them together, overall that doesn't look very good. If you have enough dependencies, your overall availability is going to be in the low double digits, sometimes single digits. That's completely unacceptable. And so what you want to do is to architect your system in such a way that your applications are isolated and protected, that any one or multiple service dependency failure will not result in a loss of user of quality experience. And this is exactly what Hystrix library allows you to do. If we dissect in a little bit more detail, for each of your dependency calls, which you inherently cannot trust, you're able to decide whether such call is synchronous or asynchronous. You're able to decide what to do in a case of failure. Will you just propagate the error up? Will you retry? In that case, what's your retry timeout and how many? Or will you provide a fallback experience? And you're able to do it at granularity for each of those calls. And together with a ribbon library, this is a very powerful tool, because as you create a new dependency, you just wrap it in a Hystrix circuit breaker, and that's it. You are protected from that new dependency failure. You don't need to go and figure out all possible corner cases that this may generate in. Together with the Hystrix library, we actually open sourced a Turbine Dashboard. It's a real-time view into your service health and its dependencies. You will see such information as the volume of the calls that you're sending to dependencies, just in case if you're having a thundering herd going through. You will see the relative health. You will see which circuit breakers are open, which ones are closed. And you can very quickly figure out how your system is healthy overall. All of this together provides really powerful tools to improve, well, give it transparency, first of all, and then improve your availability once you start using them. Again, in a startup life, time is precious. And so what you really want to do is maximize your developer's time focusing on your application and nothing else. And so any tools that improve developer productivity are a godsend. Now, tell me if that happened to you ever. You have a system running in production, suddenly part of a whole of that system become unhealthy. One of your developers says, not a problem. I'll enable debug logging and we'll figure out what's going on. And by virtue of enabling debug logging brings the whole system down because the increased load that debug generated basically took the system over the tipping point. We had a few of those. And so we developed Blitz4j on top of Log4j to make the logging better and more asynchronous. What Blitz4j does, it does better handling of the messages during the storms, exactly during the times when you need those log messages, when you need to see them. It replaces all the synchronous operations in Log4j with a more appropriate concurrent data structures that you can call asynchronously. It provides you with extreme configurability. At runtime, you're able to change the appenders, modify them, regex patterns as you see fit. And most importantly, it isolates your application threads from the logging threads. So even if in the event where you're sending obscene amount of information to the logging and there is a backlog, your application performance will not be affected. Anybody who ever developed in Java knows that at some point or another, you're going to have to deal with garbage collection. At some point, your memory footprint will be large enough that your garbage collection will no longer be unnoticeable. And for such situations, we developed a garbage collection visualizer, or GCViz. We find it extremely convenient. Many of our system runs with tens or high tens gigabytes of memory. And so we don't, in any of our systems, we don't want to stop the world type of garbage collection. And so what GCViz allows you to do is very quickly channel fairly raw and detailed and really non-human, eye-readable JVM information into such graphs. And then what you can do is very quickly iterate. OK, if I make this configuration change to JVM, or if I make this code change to my application, how does my GC profile change? You can very quickly figure out the causality, what actually causes your GC issues. You very quickly can iterate and get clarity of what's going on, fix the issue, and move on. Now, most of the time developers work on production systems, on something that's user-facing, fulfills user needs. Some part of the time they have to spend developing the tooling so they can actually get insight and perhaps operational insight or data insight into the applications that they actually develop. What we found is that without good framework, each developer, each team would end up creating their own set of tooling. Sometimes they would overlap, sometimes there would be duplication of work. And so that's why we created this framework called Pythias. It's another Greek name for some famous Greek explorer, apparently. It's a tooling framework. And it's also based on a whole bunch of other open source components, such as Juice and Jersey and D3, that allows you very quickly, with very minimal effort, create really powerful dashboards. This example that you see here is one of our dashboards for our Cassandra clusters. This way we can actually get a unified view of 60-some clusters that we run all at the same time. We can see their health. We can see whether we're running any maintenance operations, repairs, compactions, doubling, etc. The same framework allows you to create very quickly your data insight. For example, if you want to explore data that you store into S3 or SimpleDB or Cassandra, or you want to create a really powerful entry forms. For example, Archaius, the configuration management console was created in literally minutes using this framework. So we find this, the framework very useful because you never know when you're going to need to create a new tool. Might as well get something that works for you and really, really fast. Functional reactive programming is the programming paradigm that's really been gaining popularity. Many of our developers were inspired by work done at Microsoft by Eric Meyer, creating a original version of Rx in C#. And so they created and then open sourced RxJava, which is the Java, you can also use it in Scala, version of the functional reactive approach. If you've done multi-threaded concurrent programming, you know that it's very easy to get to a situation where you actually lose data consistency or you get yourself in a deadlock situation. Functional reactive takes a much simpler approach to concurrency. It's using observable pattern to create a single state upon which that you can create higher level objects for composition, but it's all inherently concurrent. And then you can really specify things like when you have a call into observable, you can Do you return from a cache? Do you go to a remote resource? And all of that instead of using your familiar threads and multi-threading and locking, all that fun. As Adrian mentioned, big data is a hot topic these days, but really, even if you're a small startup, very soon you're going to accumulate enough data that you'll want to analyze. Very typically, that's done using Hadoop, MapReduce, or similar tools. You may be running EMR on Amazon. You may be running a combination of Hadoop clusters. At Netflix, we always constantly run some sort of analytics jobs. Now, for the people who you want to analyze data, you don't want them to become Hadoop experts per se, right? They just want to send in their queries, and they want to get their data. They shouldn't care how many clusters you're running underneath. Is one cluster healthy, one cluster unhealthy? They shouldn't care how big the cluster is. And for that purpose, we created Genie, which is our Hadoop as a service. And it abstracts not just Hadoop, but also Hive and big jobs. It abstracts it with one very simple API. And with that API, you're able to submit your job, schedule your job to run at a certain point in time, and get your results without actually needing to understand how does infrastructure look underneath. And that frees up the people who run analytics to only care about analytics, really focus on the core competency of their job without being distracted by all mechanics underneath. Similarly, Pig is a very popular query language for Hadoop. We applied some lipstick to it, and what it is basically a really powerful visualization on top of some super complex Pig queries. We got to the point where some of the Pig queries that our analytics people needed to run were multi-page, very complex structured code. It was just impossible to maintain and debug. With this visualization, it's very intuitive, and you can very quickly find inefficiencies or errors in your Pig queries before you actually had to go and run a 24-hour job just to find out that the data out was garbage. All right, so these are most of the components that we open source so far. And some of them may be easier to adapt than the others, but how do you put the whole thing together? How do you make it work for you? There are several applications that provide you with a blueprint. Makes it much easier to start. One, we open source the sample application of RSS Reader. It's fairly simple, but don't let simplicity fool you. It actually pulls in a lot of the complex infrastructure together and show you how it interacts in a fully functional application. It uses Eureka service to tell where the services are. It uses Archaius to do dynamic configuration. It uses Hystrix to provide availability and resiliency against dependency failures, and so on and so forth. It's probably the best project to start on if you're just ramping up on Netflix open source components. It's going to give you step-by-step entry points into understanding how the whole ecosystem really works. There are a couple of others that were created by third parties. One was created by Chris Fregley, who used to work at Netflix. It's called Flux Capacitor. And it's a great mashup application that uses pretty much everything that we open source so far. When we open source something new, he incorporates it into a Flux. So again, it's sometimes just you want to get a snippet of how to use a component. That's one great example. Another good example was made by IBM. So they had this fake airline reservation application called Acme Air. And what they've done, they've substituted a lot of in-house built components with the NetflixOSS ones. And then they run a whole bunch of benchmarks to show how it scales. And for us, everything has to scale to a web scale, because we handle a pretty insane amount of traffic from time to time. And so, again, that's an interesting application with some good use cases of many of our components. You should go and check it out. We don't ask people who use it to tell us that they use it. It's all free available on GitHub. Some companies got back to us and actually thanked us for open sourcing some of these components. And these are some of the companies that actually wanted to have their logo on our open source site. Might find some of these logos familiar. So in takeaway, startup is always fighting against time. Your velocity and your agility is your advantage. You can use Netflix open source components to make your startup scale, go faster, or actually reinvent your enterprise. We definitely want to hear from you if you use it, what you think of it. we do encourage you to contribute to it. We hope that together we can build an ecosystem that will strengthen all of these and make them evolve, and everybody will benefit from that. You can stop by our booth at the show floor, and if you want to talk to us about any specific components. If you like this talk, we actually have a whole bunch of more Netflix talks happening today, tomorrow, and Friday. We're going to be talking about the big data, multi-regional resiliency, monitoring at Netflix scale, and a whole bunch of other things. So I encourage you to check it out. All right, so on behalf of all of Netflix team that participated in open sourcing, I want to thank you. And we are looking to your feedback.